He kōna I purangi tēnei nā te reo irirangi o Aotearoa.
Sorry, I hope I'm not in the way of any of the instruments. It's a bit tight in here.
Sorry, it's a little bit tight to this console, but one thing is when you've got lots of equipment in the van, you go very slowly over speed bumps.
And we spent the first few times, there were lots of rattling noises in the back there and we got really worried about it, but we've sorted most of them out now, but there's still a few things that squeak.
Kia ora, nau mai hara mai ki te ao hurahanga. Hello and welcome to Our Changing World. Ko klek and canon tēnei. My colleague William Ray is jammed into the front of an electric van. If you live around Wellington or the Hutt Valley, you might have seen it driving around recently. At first glance, you might mistake it for a bog-standard white tradies van. But if you looked a bit closer, you'd see all sorts of weird devices coming out of the roof. And if you got even closer than that, you'd see the branding on the side isn't for a plumber or an electrician. It's for GNS Science, now merged with NIWA to become Earth Sciences New Zealand. And if you open the door, instead of seeing racks of tools, you'd see a bewildering array of plastic piping feeding into various complicated bits of equipment, with air compressors jammed in next to big racks of heavy batteries and computer readouts. It looks just like a scientific lab. And that's exactly what it is.
So this is our Carbon Watch Urban mobile laboratory, and it is full of instruments that are going to measure greenhouse gases as we drive around towns and cities and in between towns and cities in rural areas in New Zealand. So clearly we needed to have an electric van because otherwise we'd be measuring our own tailpipe, which is not that interesting. But B, we really feel like if we're going to go out there and measure emissions, we should be walking the talk.
This is Dr. Jocelyn Turnbull. She's a principal scientist at Earth Sciences New Zealand. William met her a few weeks back to join her and her colleague Hayden Young for a spin in the mobile lab. And William was in the middle of making this episode when his gorgeous baby son decided to arrive unexpectedly early. So, congratulations, William. Thanks for the audio. And I'll be guiding you through his day instead. It begins at the National Isotope Centre in Petone and a tour through the van's gadgets. Here's Hayden.
So the van is outfitted with 4 main pieces of equipment. We have our Picaro, which is measuring carbon dioxide, methane and carbon monoxide, so you can actually see it on the screen.
Oh, whoa,
so
right.
You can see it in live time.
So that's actively monitoring right now then?
Yeah. And you can see the CO2 is pretty high because we're in a room, so the CO2 builds up and is visible by the instrument.
Right, okay.
That's our probably main instrument. We also have an instrument that measures black carbon. So that's
like soot?
It's basically anything that any combustion reaction produces a bit of black carbon. So our main use for it was we'll be able to distinguish CO2 produced by wood burning from other sorts of CO2 that we'll be measuring in total with our Picaro.
Right. So, I mean, there's a lot of stuff in here. It's like the whole back of the van's full.
Yeah. So for our instruments, it's not just the instruments. We also have lots of pumps that pull air in from outside to the instruments. We have things like drying traps. Water is a huge problem for our instruments, so we need things to pull the moisture out so our instruments can run effectively. So yeah, there's quite a bit of stuff that goes on that's not just the instruments themselves. Yeah.
I mean, how long did it take to get all this set up?
It took about 6 months to a year.
Wow.
So a lot of work has gone into this. Not just me, Lee Fleming, who's my colleague, has played a huge role in this. A lot of it was waiting for things to arrive, but there's of course a lot of setup, waiting for approvals and everything. It's been a long process, but we're really glad that it's on the road and actually measuring now. So we're really pleased with that.
As well as black carbon and carbon dioxide, carbon monoxide and methane, the mobile lab is also kitted out to measure radon gas and radiocarbon decay, both of which help to understand the source of the emissions. But we'll get to that a bit later on.
We have a GPS, so we know where we are, because that's really important, because we're mapping as we go. And then we also are measuring the wind direction and wind speed again, so we know where the air's coming from as we collect samples. So on the side here, you can see a big bank of batteries. It's about 10 kilowatt hours to run all our instruments, so we can run for a full day driving around without having to recharge. So when we go to recharge, we have to charge the van and its driving stuff, and we have to charge these batteries.
Tour complete, it's time to hit the road. Jocelyn, Hayden and William cram together in the front cab. Hayden is driving while Jocelyn sits with a laptop balanced on her knees, watching 4 lines squiggle across the screen. The top of those 4 lines measures carbon dioxide.
So actually you can see how we were building up all that CO2 when we were inside. This is the last, I want to say about 45 minutes is shown here of measurement. And you see as soon as we went out of the building and now we're measuring outside air, you see CO2 drop right back down to 422, which is what we're expecting for nice clean background air right now. And of course that 420 or so ppm is way higher than it was before we started burning fossil fuels. It was about 280 and now our background's about 420, 422.
Wow.
Yep.
So how long has this been running for?
So this van, we just had it up and running in June. So
oh, really?
This is very new for us, and we've been collecting data, but we haven't got a huge number of results from this part of the project. So what we've been doing so far is just really starting to map what emissions look like around our cities. And you can see, so we're going to drive just close by where our lab is around Seaview, which is of course an industrial area. And so it includes all sorts of different things that people are doing. And we tend to see a little bit higher CO2 in some of the places, and particularly when it's not too windy. If it's a windy day, we don't see so much. But we're also going to have a drive around past the wastewater treatment plant and see if we can see the methane emissions coming off from there. So wastewater is one of your big urban sources of methane. But we also see, as we're driving around quite often with methane, we see spikes because leaks from natural gas pipelines and infrastructure happen all the time. And you see those as big spikes as you're driving around. And
oh, really?
Again, we're trying to find those. So methane, most of the methane in New Zealand is coming from our farming, from animals. But about 10% of the methane that we produce is coming from urban areas. And that in urban areas it's primarily coming from natural gas in the North Island, because we don't actually have natural gas systems in the South Island, and wastewater and landfills. And those are all things that if we know what the emissions are and where they're coming from, we can fix them. And so that's something that we really think is important. Oh, look there. There is a spike in CO. You just saw that was probably a vehicle that's missing a catalytic converter, or its catalytic converter is not working.
A catalytic converter, just for those of you who, like me, are a bit ignorant about all things automotive, is a box that sits halfway along your exhaust pipe. And it uses small amounts of precious metals like platinum, palladium and rhodium to trigger chemical reactions that turn toxic chemicals, we're thinking things like carbon monoxide and nitrogen oxides, into safer things like carbon dioxide, nitrogen and water vapour. But in older cars, these devices can stop working. And in New Zealand, there's actually no law which says they have to be functional. And as Jocelyn, Hayden and William drive along, they continue to see little spikes on the carbon monoxide sensor.
So most vehicles are producing a small amount of CO, or carbon monoxide, which is again one of our pollutants, but a few of them produce a whole lot, and that's because they don't have a catalytic converter for whatever reason, usually an older vehicle.
Wow, so that's sensitive enough you can pick up a single car driving past you. Wow. Yeah.
And there's also a spike in methane there, so a little bit of methane comes out of vehicles as well, so that's probably what we're seeing there, and you see that spike lines up. So one of the things that we can look at as we're driving along is these spikes in the different gases, and when they line up, then they're all coming from one place. But if you see them happening at a different time, then they're coming from different places, so maybe from different vehicles. And so you can start to look at those patterns to understand what kind of sources we're seeing.
It's like the three of them are playing a very high-tech game of I Spy, watching the spikes in levels of greenhouse gas and pollutants and trying to work out where they came from.
You see how that methane spike, it happened just as after we drove out and came along here, and you see it in methane but not in the other gases, so that tells us that it's something that is coming from either a natural gas leak or from wastewater or something that doesn't have an associated CO2 spike.
Do you ever let the lines company know if you're like, I'm pretty sure that there's a big leak in your pipe just here?
So we've actually, a separate project, we've been working with some of the natural gas groups, because they want to, of course, reduce their emissions, and particularly for natural gas, if you're leaking, you've got a whole lot of things. One of them is that you're leaking the stuff that you're trying to sell, so you're losing money and you want to fix it. And of course, if you have a big enough leak of natural gas, then you have an explosion risk. It has to be a really big leak to worry about that, but nonetheless, we care a lot about that. Once in a previous project when we were working in Indianapolis in the US, it was one of the very first times that anyone had tried driving around looking for methane. We came to this petrol station and the methane spiked off the top of the scale on our Picaro.
Whoa.
And we thought we better call someone. And so then the whole fire department came. It was quite dramatic.
Wow.
Yeah, fortunately nothing exploded. But as it turned out, the leak was way off the scale on our very sensitive instrument, but it was not at an explosive level. It was something they needed to fix, but not immediately.
So you haven't seen anything like that driving around Lower Hutt?
No, we haven't. We certainly see a lot of spikes, so you see small leaks, and in fact, the natural gas companies, they have an instrument that they call Selma, which is kind of a similar concept to what we're doing, but what they do is they have their inlet along the front bumper, and they're only measuring methane, and they're looking for those leaks. The instruments that we have are a lot more sensitive, so we pick up a lot of smaller leaks, and one of the things that we can see, especially if we drive around in the evening around suburban areas, you see all these little spikes. And those are because every time you turn on your natural gas stove or your on-demand hot water heater, before that natural gas, which is methane, ignites, you get a little puff of methane coming out. So something just in here, Hayden, I think, because that's the treatment plant over there.
Okay, I'll find a spot.
They pull over on Port Road, an industrial area next to the mouth of the Hutt River. While the continuous monitoring sensors in the van work perfectly well while it's driving along, there are some things which need a bit more time in one place to measure, especially radiocarbon.
So we have, of course, as we all know, as we burn fossil fuels, we are producing carbon dioxide from fossil fuels, and that's the big reason for the increase in CO2 or carbon dioxide in the atmosphere and the global warming that we see. But also at the same time, we've got carbon dioxide that's being exchanged naturally with the land. So when plants grow, they take up carbon dioxide by photosynthesis and they use it to grow. And then plants and animals and people and soils then use respiration, which is where we take in oxygen and respire out CO2, to return most of that to the atmosphere. But the amount of carbon dioxide that's going in and out of the land all the time through those processes is quite huge. On average, if you look over a year or over a decade, you find that that's roughly in balance, that natural breathing of the earth. But if you go out and try to make a measurement at any given time, you might have a very large amount of carbon dioxide being exchanged through those processes. So we want to actually be able to separate where the CO2 that we're looking at is coming from. And so radiocarbon allows us to figure out how much of the CO2 is coming from fossil fuel burning. And so that's a really critical measurement for us, so that we can separate that out, see how much is from what humans are doing and how much is natural.
Like radiocarbon dating, like the same thing you use to date.
Yep. Yeah. Exactly. So if a lot of people have heard of radiocarbon dating, so that's where you measure how old things are. So carbon has 3 isotopes. Might be getting a little too technical, but hopefully. So 2 of them are stable. They stay around forever. And then radiocarbon is called radiocarbon because it's radioactive. So it's produced naturally in the atmosphere by cosmic rays, and then it decays away radioactively over time. And so the way it works for carbon dating or radiocarbon dating is, as I said, when plants grow, they take carbon dioxide out of the air and use it to grow. And so they take the radiocarbon along with them. But then in the parts of that plant, like in the wood and anything else that is not exchanging with the atmosphere, that radiocarbon starts to decay away. So you can measure how much is left. And if you know how much you started with, you know how old it is. So what we're doing is we're taking that same concept, but we're measuring the age of the CO2 in the atmosphere. But instead of trying to figure out how old the atmosphere is, we're saying we know that it's made up of 2 things. One of them is that natural exchange, that's modern, and the other one is fossil fuels, which are so old they have no radiocarbon left. So when we measure the age, we can figure out how much came from fossil fuels and how much came from natural.
Right. But how do you do that when it's like just all mixed up in the air together? Is it just a proportion of...
It's a proportion, yeah. So one of the critical things is that you always have to measure relative to a background. So here where we're measuring, we're trying to see what's coming off this industrial area here in Seaview. But if we were to just measure this, we will see a certain amount of radiocarbon. But what we want to know is, what does this look like, not what everything in the world. So we're actually going to compare to our long-term record from Bering Head, which is just about 15 kilometres that way.
Yeah.
And that difference will tell us how much of that fossil fuel carbon dioxide came from here.
Bering Head Atmospheric Research Station, overlooking Cook Strait, is the site of the longest-running atmospheric carbon dioxide measurement in the Southern Hemisphere. It's been keeping track since the early 1970s. Measuring radiocarbon isotopes is a bit more complicated than sniffing for methane or carbon dioxide, and it needs to happen back in the lab. So Hayden breaks out his collecting flask to take an air sample.
Yeah, we'll park up and collect a flask over a full 30-minute period. And the idea behind that is, if we measure over a longer period, that gives us a more interesting mix of emissions rather than collecting it over a really short period of time.
Flask filled, it's back to base to measure some radiocarbon. And this is where things get complicated.
So radiocarbon is quite difficult to measure because it's actually very, very rare. So in carbon dioxide, 1 in 10 to the power of 12 carbon atoms is a radiocarbon.
Oh, so it's a very, very, very small number.
It's a very, very, very small number. 1 in a trillion. I think a trillion is 10 to the power of 12. So that means that you have to do some pretty special things to measure it, and that's what this lab does.
First up is cryogenic extraction, basically freezing the carbon dioxide out of the air.
So we'll open up the flask, and you can hear all the noise in here. That's vacuum pumps, and the pumps are inside cupboards to help us have less noise, but you can still hear it. So what's going to happen is that the air is going to be pulled through all these glass lines over here.
The glass tubes run in sets of spirals, sitting above thermos flasks filled with different freezing cold mixtures. The first is a mix of ethanol and liquid nitrogen, chilled down to minus 80 degrees. This freezes out all the water vapour, meaning the air that makes it through the step is bone dry. Then it's through another set of spirals. These ones get submerged in pure liquid nitrogen,
which is about minus 190 degrees Celsius, and the CO2 will freeze out at that temperature. So we're going to freeze all the CO2, but all the other gases, primarily nitrogen and oxygen, will keep going through to the pump. And critically, you have to keep the pressure in here, right? If you get the pressure too high, you can freeze out the oxygen, which is bad, really bad, because it will explode if you get enough of it. But then we capture the CO2, and all the other gases go out to the pump and into the room, all the rest of the air. And then we can take that and warm it up, and we'll put liquid nitrogen over on one of these tubes, and we'll then close off the line, open up the bit from where our CO2 is over to where we want to freeze it next, put more liquid nitrogen on, and the CO2 will all freeze over into this tube, and we'll seal that off with a gas torch. And so now we've isolated the carbon dioxide or CO2 from the air.
When you say you seal it off with a gas torch, like you literally just melt the glass to make a little...
We literally melt the glass.
That's cool.
We do a lot of cool things. We've got liquid nitrogen and gas torches and
potentially explosive oxygen.
Yep. So obviously we do think about health and safety a lot.
That's why we've got the glasses on.
That's why we've got safety glasses on.
The next step is to take the frozen carbon dioxide and put it in a mini furnace. The carbon dioxide is essentially cooked using hydrogen and iron oxide to leave behind a sample of graphite, basically pure carbon.
Okay, so now you've got your graphite.
Now we've got our graphite, and now we're going to go down and see our other big piece of equipment, our accelerator mass spectrometer.
Wow.
This is not all of it.
Now, if you thought the glass spirals and liquid nitrogen was cool and a bit scary, the accelerator mass spectrometer is even cooler and even scarier. A massive piece of equipment filling an entire room down the hall.
So we start over here. This is what we call the ion source, and you can see that it's inside a cage, and it's inside a cage because it's at 40,000 volts, and obviously when it's running we don't want to touch it. So we have this cage to protect us so we can't touch it, and in fact you'll see if we need to adjust things while it's running, we have some big plastic rods that we can stick through the cage and adjust things. Yeah.
That tone right there, it sounds to me like William is dancing the line between terrified and fascinated. Like he knows he shouldn't touch it, but also kind of wants to find out what would happen if he did. The whole job of an accelerator mass spectrometer is to allow you to separate out the different atoms in your sample. Remember, Jocelyn said there were 3 isotopes of carbon, 2 stable and 1 that radioactively decays. They'll all be ever so slightly different weights, and I mean slightly, detectable only by a complicated process with high-powered devices. But after all these steps, the team can count the number of different types of carbon atoms in their sample, which can be used to say exactly how much of the carbon dioxide in the air is coming from fossil fuels. And at this point, you might be wondering, wait, why are they doing all of this again? Well, a big part of it is getting more information on where carbon is coming from. Because while it's relatively easy to see levels of carbon in the atmosphere rising due to human activity, it's not always easy to distinguish which activities are releasing that carbon.
Some types of emissions we know quite well. Others we don't know very well at all. So one that we've talked about a bit is wood burning. So, like I said with traffic, we know how much fuel we bought. And how much, all came from overseas, right? So we know how much came into New Zealand. So estimating the emissions, at least for the whole country, is relatively straightforward. But if you think about wood burning, most of us don't go buy wood. People get it, they chop down a tree in their backyard, they get it from their friends, all of those things. And so there's not a very good record of how much is being used. And we don't have a very good sense of how much is being used and therefore how much CO2 is being produced. So that's one that we don't know much about. But the one that's really an interesting challenge is the land carbon uptake. So as you know, we have a way of offsetting emissions with planting trees. So trees grow and take up CO2 through photosynthesis and sequester some portion of that carbon for the long term. So that counts as a sink or an offset of emissions. But in urban areas, we have always kind of assumed that didn't really happen. The cities are covered in concrete, there's no trees. And of course we know that that's not correct at all. But also that then if you think about an urban area, the kind of vegetation we have and the way we manage it is very different than if you go just outside the city. So it might be different plants. And we do all this management. So, we trim the trees, we fertilize, we mow the lawns, all of those kind of things that mean that the way that urban ecology and urban vegetation behaves can be quite different to outside of the city. But we want to understand, is that urban vegetation offsetting some portion of our emissions? And right now we think that it might be offsetting a portion of it, but we don't really know how much and we don't know the control on it. And that's the case in New Zealand, but it's also the case in cities globally. We just don't know. And so we really want to get a handle on that.
Dr. Jocelyn Turnbull is actually the lead author of an IPCC report looking at this exact issue: how urban areas contribute to the broader picture of climate change.
That's really the role of our mobile lab, is to what you could say is ground truth, but maybe atmosphere truth, what the emissions really are. And so the idea is to go around as many places as we feasibly can in New Zealand and do this regularly. So the plan is to do it once every 3 months for the next 3 years.
And as it's on its nationwide road trip, the mobile lab will be making stops to engage with local communities. And that's something that's already made a measurable impact on emissions in at least one school in Auckland.
We took instruments and we put them outside school gates and we measured the CO2 across the morning drop-off. And you could see in one particular school where the first one we did, it really stood out. You can see this big peak in CO2 at school drop-off time. And then we kept measuring right through the school holidays, and lo and behold, that peak wasn't there anymore because nobody was driving and dropping their kids off at school. And so we showed that to the kids and they came up with their own ideas about what they could do. And they had this wonderful initiative, and it's so heartwarming to see all the little kids out on their scooters and their bikes and things. Instead of driving to school, they came an alternative transportation, and we kept measuring through that period and we're able to see that they pretty much got rid of that morning rush hour peak.
Really?
Yeah.
So they sort of bullied their parents into letting them not be dropped off by car.
I guess that might be the way you put it.
like it was funny driving around, and I think I described it as sort of like high-tech I Spy. It's like, it's fun to sort of see, I mean, you know, it's slightly harrowing in other ways, but like it's really interesting to be able to be like, oh, that, I can see where that source is coming from. I know that it's that car. I know that it's like probably that power station or that water treatment plant we're driving past, that's where that is coming from. It's really interesting to actually see it live.
Yeah, exactly. I mean, for me as a scientist, I think that's the best bit of science, right? It's discovering these things that you wouldn't have known otherwise from these measurements that we can make.
Thanks to Dr. Jocelyn Turnbull and Hayden Young of Earth Sciences New Zealand. And of course to RNZ producer and new dad, William Ray. This episode was recorded and written by William Ray and produced by me, Claire Kincannon, with help from Ellen Rikers. Sound engineering was by William Saunders. You can get in touch with us by emailing ourchangingworld@rnz.co.nz or learn more about this story by checking out the show notes for this episode. Tēnā koe I whakarongo mai. Thank you so much for listening. I'm Claire Kincannon. Have a great week. Kia pai, te wiki.